Hello, everyone. Good morning. Over the years, Booking.com has grown from a small startup to one of the largest travel e-commerce companies in the world. Such growth is good for the business, but at the same time, it's a challenge for our engineering teams to scale the infrastructure. Most of the systems designed at Booking.com last a few years, and after that, they need to be re-engineered or re-architected to accommodate the growth. Our load balancing platform is no exception. So during this talk, I'm going to share with you how we scaled our load balancing infrastructure from a pair of load balancers to hundreds of load balancers, handling billions of requests a day internally and externally. So in 2008, when I joined Booking.com, our load balancing infrastructure looked like this. We had a pair of Linux boxes running IPVS, so it's IP virtual server. It's a load balancing solution in the kernel, provided some module. And for failover, we use keep-alive-d, so there was like an automatic failover could take place. Later on, we started actually using Puppet in the company, so these servers were managed by Puppet. Even I think our Git history still remembers some puppetry around these boxes. So it worked pretty well. We had some problems. For example, ARP caching was one of them. When the upstream basically was caching ARPs and we did failover and the traffic was still going to the old device for some of the sites. But overall, we were happy with it. The main problem we saw with this was layer 4. So actually, these load balancers were working fine, but we wanted to do more. And that's why we ended up with F5 appliances, where these were layer 7 load balancers, and layer 7 opened up a whole world of new possibilities, which we liked a lot. For example, you could alter the payloads, inject headers, remove headers. As well, it gave us like a possibility of routing traffic. For example, in case of some condition, you can send it here or there. Again, these devices were active standby, so one was like doing the job, the other was like sitting there and doing nothing. We didn't have any orchestration around that. Later on, we started using Puppet as Puppet proxy, but unfortunately, only a certain set of objects on the device. So all those objects related to the load balancing itself, so for like a virtual servers, pools and nodes we were able to manage, but like a device-specific properties, like a users, let's say time zone of the device, we had to set them manually. So setup of these devices when they came from when we purchased them, they had to be manual, and upgrades as well. Especially at certain point in time, we had like lots of vulnerabilities discovered in the SSL, etc. So we had to kind of do lots of these upgrades. So these processes were manual. Over time, we developed some scripts. And these scripts allowed us to automate some parts of the job, but still there had to be some operator behind it doing the thing. And unfortunately, these devices were vertically scalable. So when our traffic was growing for the site, we had to buy bigger devices. And over time, we ended up with this. Essentially, we had like lots of different pairs of different generation of hardware. The way how it worked was usually like the traffic for the main site was growing, so we had to buy a new pair of devices. So we were buying the most powerful, the most expensive ones for the main site, and those which were currently used for the main site were repurposed for some other lower traffic sites. So over time, we ended up with like all these generations, lots of these hardware lying around. And we hit at a certain point that we already kind of reached the sort of top of the line where actually there was no room to grow up, and the Viprion solution from FIO, we didn't like it a lot. So we did some research and we thought like there must be a better way of dealing with the problem. So we came across the equal cost multipath routing. Equal cost multipath routing is a strategy for routing network packets along multiple paths of equal cost. When forwarding a packet, a router decides which neck hop to use based on the results of the hash algorithm. In our case, we use per flow load balancing to ensure single flow remains on the same path for its lifetime. In this case, the flow is identified by source IP address, source port, and destination IP address and destination ports. An interesting thing happens when the amount of nodes changes. So in this case, some of the flows will get reshuffled. They're going to change the path. So depending on the different implementation of the hash algorithm, ideally you want only 1/n of the flows to change their paths, because let's say you have 4 nodes, and let's say one of them died or you ticket for maintenance, and then only 1/n, so the flows which go through the node number 5 will get reshuffled to the other ones. And actually, some vendors actually provide this. Unfortunately, some other ones, at least the time when we tested it, many more flows get reshuffled. So depending on this hash algorithm implementation, you might want to check it before you go on. You want to buy some, like you go on shopping. ECMP was like we like it a lot because it allows you to do load balancing and the line rate. I suspect it's mainly due to that there's no session table, right? So usually that was like the problem with F5. It's like a limits of this amount of session, etc. Whenever your session goes up, the things get slower and slower. In this case, you have a constant speed because for every packet you apply the hash for the packet. So this is how our architecture in one availability zone in single environment looks like. So we have 2 tiers. We have layer 3 tier and layer 7. Traffic comes from the internet. It hits one of the fabric layer switches. Single IP address by default is assigned to a single fabric layer switch, even though when this switch dies, the other switches will take over automatically. So this one is like as a primary, but like if this one dies, then the flows will get automatically handled by different fabric layer switch. Then when the traffic hits fabric layer switch, then the fabric layer switch will run the hash algorithm on the flow, and it will have, because it has 5 alternative paths, and it will select forward traffic to one of the top-of-rack switches, and then again, when the traffic hits one of the top-of-rack switches based on the hash algorithm of the flow, it will have 2 alternative paths because we have 2 HAProxy load balancers behind it. Then it will, based on the hash result, it will forward it to one of the the HAProxy load balancers. In our architecture, we have different load balancer groups. So on the diagram, they are represented as like a blue and white HAProxy logos. The load balancer group is a set of load balancers which is configured in exactly the same way, and they handle the same set of sites, the same set of IP addresses. So creating such groups allows us to isolate certain set of sites from each other. So let's say if something bad happens to a certain load balancer group, it will only affect this load balancer group and not the others. Obviously, it's possible that single IP address, even though we don't do it by default, is handled by 2 load balancer groups, but usually we do it when we transition, let's say, one site from one load balancer group to the other. So for temporary, it will run through 2 groups, and two groups will handle the traffic. So in this example, we use for different sites, traffic goes like to different fabric switch. Again, the fabric switch will have 5 alternative paths. We use exactly the same top-of-rack switch infrastructure. And when it hits top-of-rack switch will forward to the blue HAProxy load balancer. We use equal cost multipath routing in combination with Anycast. Anycast is a process for routing network traffic where sender traffic is sent to a destination that is closest to it in terms of network topology. Closest could be defined as lowest cost, lowest distance, smallest amount of hops, or potentially lowest measured latency. In practice, it means that essentially client goes to the endpoint, to the load balancing platform which provides the lowest latency. So we prefer locality. You always go local. Unless the local is not available, you go somewhere else, which is the closest. So in this example, we have a client in availability zone 1. And because of the lowest cost, it will go to the load balancing platform, which provides the same service as other availability zones, and then will be handled by the servers in the same availability zone, so that provides lowest possible latency. Additionally, when, let's say, the load balancing platform goes down, or servers are not, or it's not available, or load balancing platform is down there, then it will choose the next closest availability zone service in the next with the cost 2 in our example, and it will be handled by load balancing platform in availability zone 2 and servers there. So this will provide us automatic failover and resiliency of our service. So this is our architecture and the data plane. To manage that, we've built our own software. We call it Balancer. This software is used to manage our whole load balancing platform in the whole company. Obviously, we have different sort of clusters to handle different environments, but this is like the same piece of software. At the center of the software, we have Balancer API, which essentially stores the whole configuration in the database, and the configuration is stored as objects with attributes, and as well with a relationship between those objects. So for example, we have load balancer objects which correspond to the physical load balancers. We have virtual servers which correspond to HAProxy frontends. We have pools which correspond to HAProxy backends, servers. Business logic is a snippet of HAProxy configuration which can be assigned to either a virtual server or a pool. And some of this business logic can be context aware. So depending to in which context it gets assigned, to which virtual server is assigned, might do slightly different things. For example, if it gets assigned to virtual servers, it can actually deal with different it will actually use different set of pools, different set of backends. So basically, you build like a one logic, and you can assign it to different virtual servers, and it will do certain things. So depending on which context it's assigned, it will actually figure it out itself. Maps, access lists, and files are data files, which we store data there, and they can be used by business logic. IP addresses can be assigned to virtual servers, and SSL certificates as well we manage there can be assigned to IP addresses, and there are other various like smaller objects. So how do servers and load balancers get configured? So this diagram describes basically the whole flow, how the server essentially ends up in the configuration, how the server gets from the point when it gets provisioned to the point where it actually gets traffic. So our servers are kept in the server inventory, where basically some of them are racked, so available for use. And somebody basically comes and wants to provision one server to be a web server for specific to handle traffic for specific service. So somebody comes to the user interface and clicks that I want to provision this server as a web server. At this point, the server inventory will send an inventory update to Balancer API. So this is our brain for our load balancing platform. In this inventory update, we will get name of the server and some attributes like IP address of the server, and also attributes like name of the potential cluster the server belongs to, the role server it belongs to, and availability zone. Every time we provision a server, we don't want to manually go to every pool and say like add this server here, add this server there. The way how we solve it is by when we create a pool, we give it a specific set of attributes like a role, availability zone, and potential clusters. And these attributes you can think about like a set of rules. If this newly provisioned server an inventory update sent to the Balancer API, and these attributes of the back of the pool will match the attributes of the server will get automatically added to that pool. So we want two things happen automatically. So every time some new server gets provisioned, it will automatically get added to all relevant pools it's supposed to be in. When the server gets added to the relevant pools in the Balancer API, then the server gets provisioned, operating system gets installed, and then Puppet kicks in to configure the server. At this point, Puppet will request configuration from Puppet Master, and Puppet Master, on behalf of the server, will request server membership for specific pools the server is in, and then it will configure Zookeeper agent, which will run on the server. So the role of the Zookeeper agent is to make sure the service provided by the server is okay, so the server is healthy, so server can handle live traffic. So Zookeeper agent will run on the server, and then once it makes sure the server is healthy, it will register to Zookeeper under specific namespace, which was configured by Puppet. This namespace is watched by Zookeeper to Balancer. It's a separate daemon which acts as a proxy between Zookeeper and Balancer API. So essentially, it proxies the information from Zookeeper into the Balancer API. So once it will see the MFRL node of the specific server in specific namespace, it will enable this server in the Balancer API for specific pools. So at this point, server gets enabled. Initially, when the server gets inserted through the server inventory, the server is disabled by default for a good reason. We don't want any server to get traffic by default, right? We only want it to get traffic when we confirm it's healthy, everything's fine. At this point, the information gets propagated through Zookeeper, and then the Zookeeper to Balancer will enable that. At this point, the server is ready to receive live traffic. Similarly, when say, health check fails or server goes down, then the MFRL node gets removed from Zookeeper, and then this information gets propagated to Zookeeper to Balancer, and Zookeeper to Balancer will remove will disable the server in Balancer API. So this is like how the information is stored in Balancer API, but how this information gets propagated to the load balancer. So on every load balancer, we run a Balancer agent. The role of the Balancer agent is essentially to configure all the components and get configuration from Balancer API and configure relevant components of our load balancing platform. In this case, a Balancer API will periodically check for configuration changes and will first configure HAProxy software. So it will configure it. The configuration can take place in two ways. If the configuration change can be applied over the socket at runtime, it will do that, and then it will update the configuration file. If the configuration is not supported over the socket, or there are too many changes, for example, I don't know, 100, whatever, so it will fall back to the reload. So update the file and then schedule reload of the HAProxy. Once the HAProxy gets configured with all the relevant services, Anycast health checker will get configured. The role of the Anycast health checker is to essentially make sure that all the services which are configured on HAProxy are healthy. So actually, it will check all the services behind single IP address. Once all the services, because behind single IP address, we can have multiple services. Let's say we can advertise, we can provide HTTP, HTTPS, or in some cases we provide like a SSH, for example, like for GitLab, for example. So in this case, once Anycast health checker will confirm all services behind a single IP address are healthy, it will reconfigure a BIRD BGP routing daemon, and BIRD will start announcing this prefix or this IP address to the upstream. In our case, it's a top of rack switch. Then when the top of rack switch will receive this advertisement, all the traffic will start flowing for this specific IP address to HAProxy load balancer. So this is our load balancing, and then HAProxy will forward this traffic to the backend server. So this is our load balancing platform. We need as well a good visibility of that. So we have extra daemons running on the load balancer to make sure we have good visibility what is happening. So we have created HAProxy stats daemon, which periodically dumps the information from HAProxy over stats socket, and we'll submit it to Graphite. Similarly, collecd is running on the box itself as well to collect operating system specific metrics and submit them to Graphite. These metrics can be used, for example, to build some nice dashboards or to set up some, let's say, boson monitoring if certain metrics go below certain threshold, etc. Additionally to Graphite metrics, we send access and error logs to rsyslog over UDP, obviously, to not block. And then local rsyslog will forward these log messages to central logging system, and then eventually they're going to end up in Elasticsearch cluster, where they can be analyzed, and then we can build some visualization, do troubleshooting, etc., because then we have on per request logs. Based on the data stored in Elasticsearch, essentially we can see different things. It's up to you to decide what actually you want there. HAProxy has plenty of different features, so what you want to actually dump there, it's up to you. There are lots of data. So in our example, you can see that you can compare different TLS. What is the TLS handshake time for different TLS versions? The variability for TLS 1 and 1.1 comes from the fact that actually majority of traffic these days is TLS 1.2 and 1.3, and we don't have enough samples for TLS 1 and 1.1, and that's the graph is a bit jumpy. Additionally, you want to make educated decisions based on the data you store there, whatever you want to enable TLS resumption or not, and how much gain you can get from enabling that. At Booking.com, we aim to provide load balancing as a service. So that's why for the balancer, we created multiple user interfaces. So people who do not know much about load balancing can actually use our service, our load balancing platform. So the first user interface we created is a visualization tool. You have a screenshot on the screen. This user interface allows people to actually see how the configuration looks like, so that basically visualize it, and as well click on the relationship, so then they can see how the objects are connected. So if they can find object, then you can kind of follow the relationships. And as well, we allow them to change attributes, so they can actually modify the configuration at runtime. So they can go there through the UI and then just send a changing ratios or whatever. So they can do it. Obviously, we limit the scope of the actions to the roles they maintain. So they can only manage their own services. We also created a create pool and create site user interfaces. I'll talk about it in a second, which they allow them to create configuration for the newly built services. Additionally, we created a failover traffic user interface. Failover traffic is for basically easy failover traffic between different availability zones in case of an outage or bad rollout or servers being down. So in a very easy way, then basically they just click one button and the traffic will just get away from certain availability zones. We also provide them access to logs and metrics. So if they want to troubleshoot problem regarding their service, they can go directly to the data, or if we provide a set of dashboards with a generic dashboard, but if they want to build their own dashboards with custom stuff, we provide access to metrics directly. So for the role owner to create their own service, first they need to create a pool. So first they have to specify a role. The most important attributes is a role, availability zone, and potential cluster. So these three attributes will describe which servers are going to end up there. So once the user selects that, in the members field, he will see which currently present server in the server inventory will actually end up in that pool. So if he's happy with the results, if actually these servers should be there, basically he will click create create pull button, and the pull gets created. Once he has a pull, then he can proceed with a create site user interface where he first has to select a role for which he wants to create a site. By site, I mean that's like a multiple virtual servers which are configured in multiple availability zones at the same time. So basically, they're available, let's say, through all our infrastructure. Then once he selects a role, he can select the pools he wants to use for that site, some other mandatory attributes, and then click validate button to actually validate if he's happy with the changes which are going to take place. He's happy with that, he clicks the create site button, and his site gets created in a short while. He basically can just use it right away. One of the biggest features which we developed on top of HAProxy, which was actually developed as a context-aware business logic, is smart traffic routing. Smart traffic routing is a business logic which has 3 requirements in mind. So first requirement is that we want traffic to be delivered whatever possible. Obviously, we prefer always go to the local server. So due to the lowest latency, we always prefer a local availability zone, or to go to the local, let's say, local servers. But if that's not possible, use the servers whatever they are. I don't care which availability zone, please deliver traffic to those servers if they are healthy. It's always better to serve slow response rather than returning errors to the customers. So we aim to never fail. The second requirement is that we always want even traffic distribution between different availability zones. This requirement comes from the fact that if you're dealing with lots of servers, then actually if availability zone 1 in our example goes down, and then Anycast will send it to the next closest availability zone. In this case, will be availability zone 2. So that means this availability zone servers will receive twice much traffic. If you would evenly distribute it between the remaining availability zones, these servers will all servers will only receive 50% more traffic. So if you are dealing with a lot of servers, 50% versus 100% means a lot of hardware. So this requirement tries to actually more efficiently use your hardware and have lower capacity requirements for every availability zone. And the last requirement is we want our clients to get sticky to specific availability zone. This requirement comes from the fact that is due to the session data, because when the client hits to specific servers in a specific availability zone, his session data gets stored locally, and as well it gets synchronized to other availability zones. If he will flick between different availability zones on per request basis, there's a race condition between the data being copied, his session data being copied from the previous request from a remote availability zone and then the session data being stored for the current request, and then his session data might get clobbered, or some data might be overwritten. I mean, our software can deal with that, but we would rather avoid it rather than deal with it. So in normal circumstances, traffic gets evenly split between all 3 availability zones. Then it hits a load balancing platform in that availability zone, and then hits servers. So this is like a normal circumstances. In case of load balancing platform failure in availability zone 1, thanks to Anycast, traffic from availability zone will hit a load balancing platform in availability zone 2. Then a load balancing platform in availability zone 2 will see this is the traffic meant for availability zone 1, and servers in availability zone 1 are up. In this case, it will forward traffic back to availability zone 1. So in this case, the event traffic distribution requirement is met. Obviously, we have extra latency for the traffic going through availability zone 1, but everyone is happy, I guess. In case of servers being down, similarly to the previous diagram, traffic, again, will flow to the load balancing platform in availability zone 2. But then, load balancing platform in availability zone 2 will see that servers in availability zone 1 are down, and then it will split this traffic evenly between all remaining data centers. The traffic which goes directly to availability zone 2 and 3 just remains as is. We only now basically splitting traffic between availability zone 2 and 3, and as well we try to keep clients sticky to specific availability zone. So these are the failure scenarios, and more common scenario is this, which is similar to the previous one, where actually load balancing platform is up, but the servers are down. This could be due to outage being in availability zone 1, or servers being, or like a bad rollout there, or somebody doing a failover when he basically marks all these servers as down. In this case, the load balancing platform in availability zone 1 will distribute this traffic among remaining availability zones. So, what are our current and future plans? Currently, we are in process of evaluating Intel Quick Access technology to do SSL acceleration. So we want HAProxy do SSL offloading in hardware. So we already have a proof of concept, and we are basically need to run some tests and get some numbers to actually see how much benefit we could get from the hardware acceleration. Our platform is HTTP2 ready, but we run into some problems, and we first need to sort it out before we enable it globally. Obviously, we're looking forward for HTTP3, which is upcoming new protocol. And as well, one of the features we were asking HAProxy for was TCP fast open on the backend side, because TCP on the front end was available for quite a while. But this is something we would love to try it, because we have some setups when actually the latency between the HAProxy and the backend server is relatively high. And this would allow us to significantly reduce connect time for all consecutive requests. And as well, we want to provide path-based routing in the balancer user interface for role owners. So role owners can actually define their routing rules for their service. So how they want for specific path, where they want traffic to go to. So this will allow them to basically specify their own through the user interface without much knowledge of like a balancer API would do, through a simple way to define, like, for this path, go here, for this path, go there, etc. In our load balancing platform, we use the following open source software. I have to mention that the bottom three, so anything below Bird Internal Routing Daemon, was exclusively created for our load balancing platform. You have to keep in mind that some of these can be like a partial obsolete or might be obsolete soon. This is due to the fact that actually when we created our load balancing platform, we were dealing with HAProxy 1.5, which was a while ago. And some of these functionality actually, HAProxy moving forward and basically listens to its customers and implementing some features which people are using. And now I will be happy to answer your questions if you have any.
OK, thank you so much.
Thank you as well.